In this video, we are going to compare discrete and continuous random variables. We know random variables, they are functions from the underlying sample space to a set of numbers. And in this course, we mostly discuss about the real value random variable. So real valued functions. There are so many functions, right? And we focus on two types of functions here, the discrete one and continuous ones. So discrete random variables and continuous random variables. What are the connections? What are the differences? So for real valued random variable, if we look at a discrete random variable, the support of this random variable, or you can consider as the range of this x function, right? Essentially, the range of this x function or the support of this discrete random variable x is a list of numbers, right? Suppose here we list all possible numbers that could be taken by this random variable x in increasing order, so x1, x2, xn, and keep going. We can see that the interior of this set is empty, so it contains no non-empty open intervals. Well, for the continuous discrete random variable, if you look at the range of this y function or the support, which is also the support of the continuous random variable y. If we regard y as a function, then this is also the range of this y function, right? It contains open intervals. For example, it could contain some open interval, for example, a and b. So the interior of this set, interior of possible values that could be taken by this continuous random variable y, is not empty. It contains open intervals, open sets within the support. Furthermore, if you look at how do we describe the distributions of those random variables, we have CDF well defined for both cases, right? What is the CDF function? That is essentially describe the probability of event of such type. The random variable is smaller or equal to a given number. So for discrete random variable, we have step function. Those are right continuous functions and remains constant in certain interval and then sudden jump. These are also increasing functions from 0 to 1 with jumps, right? So if you recall the figures we have, it looks like this, right? A suddenly jump and perhaps jump again and increase from 0 until 1, right? After it achieves 1, it's always 1 afterwards. Well, for the CDF function for continuous random variable, we have a continuous and even differentiable CDF function. And they are also increasing from 0 to 1, but there is no jumps and differentiable. Particularly for this one, you can even find, well, a density function such that this CDF function fy can be written as the Riemann integral of the density function. So indeed, they also have a specific way of describing the distributions. For discrete ones, we have probability mass function. For the continuous random variable, we have the PDF function, the probability density function, right? This one is defined for discrete, and this one is defined for, the PDF is defined for the continuous random variable. What is the PMF function? Well, that is essentially the probability of x equal to certain values. So the PMF function can also be calculated by CDF because we know CDF also describes the distribution, right? Here we order all outcomes in one increasing order, so this PMF function, probability mass function, evaluated at point xi is essentially the difference in the CDF function values, fxi minus the fxi minus 1. It can also be rewritten as the difference between fxi and the left limit fs with s approaching to xi from the left. For discrete random variable, this left limit is essentially equal to the same number of fxi minus 1, given we are order all possible outcomes in one increasing order. And the CDF function here, right, fx for discrete random variable basically is to sum all the probability mass functions with xi that is strictly smaller or equal to x. Okay. And for the probability density function, it also has two properties to satisfy. So first is non-negative and strictly positive if x is in the support of x or the range of this x function. And the sum of all the PMF function values evaluated with xi from all the range of x, the support of x, is equal to 1. So here for this density function, we have an additional implicit property here. The probability mass function here, we have an implicit property here is strictly smaller than 1 or equal to 1, right? Given the summation of them is equal to 1, we know each of them need to be smaller or equal to 1. For the continuous random variable, continuous real values random variable, we have probability density function, which is normally taken as the first derivative of the CDF function. Or it can be rewritten as this way, right? This is essentially the definition of the first derivative of the CDF function. So Fy, right, similarly can also be rewritten as two format here, right? Here we have differences of CDF functions equal to the PMF, and here we have the derivative, differentiable derivative of this differentiable CDF function is equal to the density function. Again, from the density function, we can also recover the CDF function, which is simply to integrate Fy, the small fy, the density function, for all values that is smaller or equal to y, right? Whether to include an equal sign here does not matter, because we know increase or decrease the value or include one point, a single point inside the integral or not does not change the value of this integral, Riemann integral. So again, for the density function, it also has two specific properties. It's non-negative and strictly positive for any points within the support or the range of this y function. And the integration, the Riemann integral of this density function from, well, the negative infinity to positive infinity is always 1. Or you can simply integral over the support of the random variable, because all outside of the support is simply 0, right? It doesn't matter what happens there. But different from the probability density function, even though they are both non-negative, this one is upper bounded by y, by 1. But for the probability density function, it could be possible that it could take values that is strictly larger than 1. Okay, so it's not upper bounded. And of course, we have also discussed about the expectation of real valued random variables. For both cases, we have expectation defined based on different format of the distributions. We know in both cases, we can calculate the expectation based on the CDF function. For the discrete random variable and for the continuous real valued random variable. Of course, for this one, this integral is a generalization of the Riemann integral. So it's slightly more complicated than the simple Riemann integral. The formal definition we start with for the discrete random variable is simply based on the PMF function. PMF function is only defined for discrete random variable. So here is a weighted sum of all possible values that could be taken by random variable x weighted by the probability mass function. The probability value of random variable x equal to that certain outcome, a certain value. Right here as well, for continuous random variable, the formal definition we have where the Riemann integral is the Riemann integral of y weighted by the density function, and we're gonna integrate over all possible values taken by y. Or you can simply integrate over negative infinity to positive infinity. But outside of the range of y, or outside of the support of this random variable y, this density is always set to be 0, so it doesn't matter what happens outside the range of this y. Okay. Specifically, for a very special case, for non-negative integer valued discrete random variable, there is one alternative way of calculating the expected value, making use of the survival function. The survival function, gx, is simply 1 minus the CDF function, fx, 1 minus fx. So for arbitrary value, small value, small x, gx small x is equal to 1 minus fx small x. This is the survival function. And similarly, we're gonna have for continuous random variable, this is also true, right? But from the summation, we're gonna making use of this integration. Now let's discuss the connection between these two types of random variables by looking at this alternative way of deriving the expectations and see what we can deliver. So if we have x be a non-negative integer valued random variable, then if the expectation exists, it can be rewritten. The expectation can also be calculated via the survival function. And the summation of the survival function evaluated at each non-negative integers and sum them together. The proof is straightforward, right? So if we look at the proof, this is the first key step. Note that the x random variable, this x function, is essentially equal to the summation of this indicator random variable, or the summation of the indicator functions. This above holds true because x, the left-hand side and the right-hand side, are the same function from the underlying sample space to the set of non-negative integers. So if x, for example, if xs equal to 2, then apparently only the first two indicator functions will be equal to 1. So the summation is also equal to 2, right? So the left-hand side is always equal to the right-hand side. And no matter what values this x takes, it could be equal to arbitrary n. And you see there's only n indicator functions equal to 1, and the rest will be 0. So the summation of these indicator functions will also be n. The left-hand side is equal to the right-hand side. Then we can apply the linearity of the expectation fundamental bridge and the fact that given x only takes non-negative integer values, those two events are equal to each other. Then by taking expectation on both sides of this identity, we can find these results. Right? The expectation of x is essentially the expectation of the summation of the indicators. Now, if the expectation is well defined, we can exchange the order of the summation and the expectation. So the expectation of the summation is essentially equal to the summation of the expectation. And by fundamental bridge, we know this expectation of this indicator function x strictly larger or equal to I. is equal to the probability value of x strictly larger or equal to y. And given these two events are the same, so we can rewrite a little bit as a different summation over there, which p, the probability value x strictly larger than I, that is essentially the survival function for this discrete random variable. Now, what would happen if we consider non-negative real-valued random variable? Right? It could be either discrete or continuous, as long as it's non-negative real-valued random variable. Then, if the expectation exists, it can be rewritten then as this formula, as this integration of this survival function. Note this case also contain the case of discrete random variables. Well, this is true because we can decompose this Riemann integral by first integrate from 0 to 1, and then integrate from 0 to 2 or 1 to 2. We sum them together, and 2 to 3, and we keep going. Okay, so it's the same. This will give the same integral value if this expectation is well defined. But what is the first integration? What is this first Riemann integral value if x is non-negative integer valued? If x is discrete and such that it's a non-negative integer valued random variable, we know this survival function evaluated at 0 and 1 is essentially a constant gx0. Right, so the first term is integrate this constant over 0, 1 of unit length. So the first term will be equal to jx0. And same for the second term will be jx1. And we keep going. So essentially, we deliver the same results as shown on the left panel of this slide. So indeed, this is a more general formula than the formula shown on the left-hand side of this slide. The question is, how do we prove this result? You can pause the video at this moment and try to think about it. Well, the proof is again by notice this identity. If x is a non-negative real-valued random variable, we can generalize the identity on the left panel to this case. This one is a better formula, nested, well, not necessarily better, but a general formula that holds true for non-negative real-valued random variable. Why? The arguments is similar. Again, the above holds true since x, the left-hand side of this identity, and the right-hand side of this identity, a Riemann integral of the indicator function, are essentially the same function from this underlying sample space to a set of non-negative real values. Right? Let's think about this example. When xs is smaller, when xs is equal to x, so suppose now the left-hand side of this identity, x maps this outcome from the sample space to x. Let's see what number would be assigned to this outcome where the function on the right-hand side of this identity. Surprisingly, it's the same number. Now, if we plug in this s, xs is equal to x. So this indicator function is only equal to 1 in the interval from 0 to x. Right? only t takes value from 0 to x is equal to 1. Otherwise, if t is strictly larger or equal to x, then this indicator function is simply 0. So this integration of this indicator function is from 0 to x 1 dt plus x to infinity, but the indicator function will be simply 0. And what is this integration from 0 to x with 1 as the integrand is simply x. So for this function, this identity also holds true. On both sides, they are the same functions from S underlying sample space S to the set of non-negative real values. And next thing is we can make use of, again, linearity of expectation or linearity of the Riemann integral and fundamental bridge to deliver the final results. If we take expectations on both sides of this identity on the right-hand side panel of this slide, okay, by the linearity of the expectation, note that this Riemann integral, right? If we recall, the definition of Riemann integral is basically a limit of summations. And we know we can exchange the order of expectation and summations, and following similar logic, we can also exchange the order of the expectation of the integral. So the expectation of the integral is equal to the integral of the expectation of this integrand. And via the fundamental bridge, we know the expectation of this indicator function is essentially the probability of x strictly larger than t. This is the survival function. So in the end, we are able to show that the expectation of x, a non-negative real-valued random variable, can also be calculated via the survival function, which is simply the integration of this survival function from 0 to infinity. Okay, next, in the following, let's discuss some additional connections and differences via some problems. So first problem, what is the probability of the event that, well, that is a random variable, equal to a certain number? The first scenario we consider is x follows Bernoulli, half, with successful rate equal to half. So it has the PMN function, the probability mass function. It's either equal to 0 or 1, and both with half probability. What is the support of x? Is simply 0 or 1, right? There is two possible values that could be taken by this discrete random variable. So finitely many possible values taken by discrete random variables, at most countably infinite. And in this case, there's only two possible values. Then what is the probability of that equal to a certain number? In this case, what is the probability of x equal to a certain number? Well, for x within the support of x, right? In this case, 0, 1, the probability of x equal to x is equal to half, and 0 otherwise. Now, what is the difference if we have a, well, continuous random variable? Suppose now we have a continuous random variable with density equal to 1 for any values from the 0, 1 interval. So for any values between 0 and 1, this one has positive, strictly positive density. And outside, for any x outside this interval, 0, 1 interval, this density is equal to 0. the support of x now is, well, the whole interval from 0 to 1. So there's infinitely many, actually uncountably many possible values that could be taken by this continuous random variable x. You can pause the video at this moment and try to think, now what is the probability in this case for the event x equal to, for example, a certain number from 0 to 1? Not surprisingly, it's actually 0, given there's infinitely many possible values taken by this random variable, continuous random variable x. Then the probability of x equal to one specific number, exact number, is always 0. Well, this is because if we look at, right, the probability, how do we calculate the probability of x equal to a specific number? It basically means, let's consider this delta goes to 0. This positive delta goes to 0, that x is strictly larger or equal to x minus delta and x plus delta. Okay, so as delta gradually drifting to 0, essentially, right, this limit is equal to the probability of x equal to exactly x. And how do we calculate this one? This one is simply the limit of this integration, right? So it's always 0. Or you can directly write down as what is the integration value? What is the integral value if we integrate from x to x with this density? Yes. Then according to the theorem of integral, Riemann integral, we also know is simply 0. So basically there are so many numbers within the support of this continuous random variables, then the probability of x picking up one exact number is always 0. You could let computer to generate random variables, continuous random variables, and if you have a mind of a specific number, you just run the computer, you see you can never guess the correct number the computer generate, right? So the probability of x, random variable x equal to a specific number is kind of always 0 for continuous version. And indeed, these results can be extended for all continuous random variables. Given there's uncountably many possible values, it is of 0 probability that you can choose a specific number. However, you can get outcomes in a neighborhood closer to the number x, right? For example, if we consider the open interval contains x, x minus epsilon, x is x plus epsilon, let x be an arbitrary and very small positive number, then the probability within this interval, if we consider x is in the, for example, if we consider x is in the open interval from 0 to 1, so the probability of x taking values in this small interval within 0, 1, suppose we assume x minus epsilon, x plus epsilon is a subset of 0, 1, then the probability of x in this small interval, even though it's small, is still 2 epsilon, which is larger, strictly larger than 0, if epsilon is still positive. Okay. Now let's summarize what we find here in one sentence. For uncountably many possible values, well, given continuous random variables, they can take so many different possible values. It is of 0 probability that you can get a specific number, right? That for the random variable takes a specific value. Okay, this is true for all continuous random variables. Let's consider the second question. What is the probability of, suppose we have 3 ID random variables here, Z1, Z2, Z3. What is the probability that we happen to have this order, right? Let's consider the first case. That xi follows IID Bernoulli distribution with the successful rate half, and thus each of them will have identical PI math function. The probability mass function is either equal to 0 or either takes value equal to 1 with half probability. Now the question, what is the probability of, for example, what is the probability of x1 smaller than x2 smaller than x3? It's not possible, right? Because there's only two numbers. If x equal to 0, then x2 has to equal to 1. Then x3, well, there is no number left for x3. So we can see that the probability of such event is always 0. At least two of them will be equal to each other. What happens if we change xi from discrete random variable to a continuous random variable? Again, let's consider xi are continuous random variables with probability density function fx a constant one, which is constant 1 within this 0, 1 interval and 0 otherwise. So this random variable big X could take all possible values within this interval from 0 to 1. Now let's consider what is the probability of x1 smaller than x2 smaller than x3. Right? They are identical and they can all take different values, right, from the interval from 0 to 1. So apparently will contains outcomes such that the first one equals, for example, 0, the second one equal to, let's see, half, 0.6, and there are just so many of these possible outcomes. And what are the probability of such outcomes? Or what are the probabilities of these combinations? First, note that they can never be equal to each other actually in this case. Because if we consider xi minus xj as long I not equal to j is again another continuous random variable, and the probability of these equal to each other is essentially means this new random variable, the difference between these two random variables, again a new continuous random variable, need to be equal to 0. However, based on the discussion of problem 1, we know for continuous random variable, this is a new continuous random variable, the probability value of continuous random variable equal to an exact specific number is always 0. It's always equal to 0. Given it's always equal to 0, we know that any two of them will be equal to each other. This is only happens with, well, never happens actually. It happens with 0 probability. So this one only happens with 0 probability. Then how do we proceed to the next stage? How do we calculate the probability, for example, of the specific order? x1 strictly smaller than x2 and strictly smaller than x3. You can pause the video at this moment and try to figure out the following. Well, we know if they cannot be equal to each other, then one of the orders has to happen. So one of the arbitrary order must happen. xa1 strictly smaller than xa2 and strictly smaller than xa3 for any permutations of a1, a2, a3 of 1 to 3. and they have identical and independent distributions, right? So each of these permutations, each of these orders would happen with exactly the same probability. How many orders do we have here? We have 3 factorial different orders. And each of these orders happen with exactly the same probability, and they are mutually exclusive events. Sum them together, they need to be equal to 1. So for each of the specific order, by symmetry, we know it's 1 over the number of possible orders, which is 3 factorial in this case. Very simple, right? By symmetry, we can deliver the probability value of such ordering with IID continuous random variables. So this is, well, kind of different from the discrete ones. And here, notice that any, well, for 2 different continuous random variables, if they are independent from each other, then the probability of one equals to another, right? Well, as long as there are 2 different continuous random variables, if their difference is again a continuous random variables, we know they can never be, well, they can only be equal to each other with probability value of 0. Here we discuss the order concerning 3 different random variables. The results can extend it to n IID, independent, identically distributed continuous random variables. And here, how many different orders we have? For n different random variables, IID random variables, we have n factorial different orders, and each of these orders would happen with exactly the same probability. And they sum together, each of these they have identical probability and they are mutually exclusive events. So they sum up together need to be equal to 1. So there's n factorial times the value they have for each specific order. The probability value of each specific order is, well, identical constant, let's name it small p. We sum them all together, n factorial times p is need to be equal to 1, right? According to the axioms of probability. Therefore, for each specific order, the probability of each specific order is simply 1 divided by the total number of possible orders. So if we summarize what we learned from the second problem again, if we have IID continuous random variables xi, then the probability of having a specific order by symmetry is 1 over n factorial. Okay, so this video discusses connections and differences concerning discrete and continuous real-valued random variables. Thank you for watching this video.